can see it now.
All right, cool. Hi everyone, my name is Sorawee, and today I am going to talk about our work on formal foundation for symbolic evaluation with merging. Server-aided tools such as verifiers, synthesizers are widely used in many applications whose correctness are very important. And so we want server-aided tools to be correct. The correctness of these tools depends on the correctness of the components in the pipeline. And so, what's a pipeline? Well, the tool consumes a program P in a language L and employs the symbolic evaluation, which is a compilation process that transforms the input program into its logical encoding. It does so by composing the interpreter I for the language L in the host language H with the reusable symbolic evaluator for the host language H. The interpreter is provided by the clients. The last component is the solver. Now, one thing that I would like to mention is that for different applications, you would have different interpreters and sometimes even different software. But the reusable symbolic evaluator is what's in common among all of these tools. And this is what makes it reusable, right? It must interact with different interpreters and different softwares. All right, so now let's come back to the issue at hand. We want the software-aided tools to be correct. And so, well, the interpreters are written by the clients. So hopefully they will test it well and make sure that it's correct. A lot of research has been put into making sure that the solvers are correct, either by testing or proving that it's correct. Can we say the same for the reusable symbolic evaluator? Can we prove that it's correct? This is what this talk is about. The main challenge is to come up with the correctness definition of the reusable symbolic evaluator. And this highly depends on the design of our reusable symbolic evaluator. In particular, because we are generating this query from running the symbolic evaluation through multiple layers of the components, we want it to be efficient. And because the interpreter that clients write need to interact with the reusable symbolic evaluator in various ways, we want it to make it easy to generate the query or formulate query. That is, we need to provide a way for the interpreter to access internal states in the symbolic evaluator. And lastly, we want our framework to be general. It should accommodate a wide range of implementations. Maybe in this application, I want to reason about integers. In another application, I want to reason with strings. I should be able to do so without having to coming up with a new design for each of these parameters. The key ideas to solve these challenges is as follows. For efficiency, we will use merging inspired by bounded model checking, and this will make sure that there is no path explosion occurs in the semantics, in the symbolic semantics. To make our symbolic evaluator reusable, we will maintain several strong key invariants throughout the whole evaluation so that clients can utilize these invariants in formulating the query. And lastly, to make the symbolic evaluator general, we come up with the concept of symbolic factory, which is a set of operations that we allow clients to customize. And finally, we can come back at the question, what does it mean for reusable symbolic evaluator to be correct? And that is, we're going to give a partial soundness and correctness with respect to the concrete semantics. Now, concretely, our contributions is as follows. We present a new symbolic semantics, SC, which satisfy the constraints that I mentioned earlier. We also give the correctness theorem for SC. These are mechanized in the Leannet theorem prover. Next, we implement two reusable symbolic evaluators based on SC. One is in the Leannet theorem prover, and we call it Leannet. Another is in Racket as a new rosette system, Rosette 4. Leannet is proven to be correct, and we make sure that Rosette 4 is correct by performing differential testing. Lastly, we port numerous software edit tools to Rosette 3 to Rosette 4. And as you will see later, this will show that the symbolic semantics satisfy the constraints that I mentioned earlier. For the rest of this talk will be structured as follows. First, I will present the syntax and concrete semantics, which we call it lambda C. And this is going to be the ground truth for the correctness of our symbolic semantics. Next, we will present our symbolic semantics, which we call SC. After that, I will talk about its correctness. And after that, I will talk about the key invariants of SC that makes it easy to formulate queries. And lastly, I will present the results and evaluation. So the syntax and concrete semantics are pretty standard. We take an existing language in the literature called call scheme and extend it by abort and error. There are various minor differences, but notably, we make the Boolean built-in because we are going to have logical constraints, and it's handy to have this concept of Booleans. Primitive operations and constants are parameterizable, and so you can specify it however you want. Lastly, we have error and abort, and this can be used for expressing assertion and assumption naturally. All right. Now for the symbolic semantics. Well, the idea of symbolic semantics is pretty intuitive. In concrete evaluation, we are doing a computation over one single value, one single concrete value, right? In symbolic evaluation, we have a concept of symbolic value, where one symbolic value represents a set of many possible concrete values. For instance, this symbolic value 2x here might represent a set of even integers, right? And by the way, I will denote these symbolic values with pink text. And again, we have x equal to 0 or x is not equal to 0. This will always be true. And so it represents a set of just true. Symbolic Boolean in particular is pretty nice for expressing the logical constraints. The process where we define the symbolic counterpart from the concrete counterpart in a way that is consistent is called lifting. Now, because we allow you to, customize all these operations and constants, we also allow you to customize the structure of the symbolic value and symbolic Boolean. Intuitively, these symbolic values should encode a kind of term language that is used in the underlying software. And lastly, there are a lot of operations that we will perform in this symbolic evaluation. We allow you to customize that as well. But of course, these are constraints that there are restrictions on how it can be implemented. So these are kind of like the contracts that the clients need to satisfy in order to implement this symbolic factory interface, so that the correctness as a whole is guaranteed. We demonstrate that the symbolic factory can indeed be implemented. We do it twice, one in the Leannet and another in the Rosette system. Now, symbolic evaluation is just like, now we can talk about the symbolic evaluation, right? So given a symbolic environment, we can symbolically evaluate it to get a symbolic result. This program here says that assuming that y is not 0, then y is positive. And so in particular, in the concrete semantics, if y is equal to 0, then we will just abort it. If y is negative, then we will error. And otherwise, we will return a dummy value. Now, when we symbolically evaluate it, we get a symbolic result. It consists of two things. The first thing is the symbolic state, which itself consists of two parts, the assumption formula and the assertion formula. And the second part is the symbolic value, true. We can see that the symbolic result is correct as follows. When x is equal to 0, the assumption formula is false. And this corresponds to how there is an abortion in the concrete evaluation. When x is negative, the assertion formula is false. This corresponds to how there is an error in the concrete semantics. And when x is positive, both assumption and assertions formulas are true. This corresponds to how the concrete evaluation results in an answer. We can make what I just said a bit more formal by introducing the concept of model, right? So given a model, we can project a symbolic environment or symbolic result into the concrete counterpart. And in particular, we say that this concrete environment is a member of the symbolic environment, and the same goes for the result. Now, with all that, we can start to formalize SC, the symbolic semantics. And this is done by lifting the evaluation rules of lambda C. Now, what I would like to point out is that we use merging. And this is very crucial for making sure that our system is efficient. And by that, I mean, it does not have the part explosion in the symbolic semantics. And again, we leave several operations to the symbolic factory in order for you to customize it however you want. All right, so that's it for the symbolic semantics. Let's now talk about the correctness of the symbolic semantics. Now, the symbolic factory interface is intuitively very weak, right? It only specifies the specification of what it can be. So it admits a wide range of implementations. And this is a good thing. This is what we want. But there's a complication, which is that there could be different symbolic interface, which has the same semantics, but it has different strength in partial evaluation or different simplification rules. And this has a profound effect when the symbolic factory is composed with the evaluation. So for instance, in this evaluation, it might terminate quickly. In another evaluation, it might take a bit more time. The answer is still correct, but it takes a bit more time. But in some other evaluation, it may not even terminate at all. And so our correctness definition must take account of these behaviors. And we do so as follows. The correctness of SC is structured so that it's the soundness and completeness in a standard way. The soundness says that the symbolic semantics is an over-approximation of the concrete semantics. In particular, for every program P and for every symbolic environment, if we symbolically evaluate it to get a symbolic result, for every concrete environment that is a member of the symbolic environment, if we concretely evaluate it to get a concrete result, it must be the case that the concrete result is a member of the symbolic result. Now, completeness is the opposite of that. It says that the symbolic semantics is an under approximation of the concrete semantics. And so for every program P, for every symbolic environment, if we symbolically evaluate it to get a symbolic result, for every concrete result that is a member of this symbolic result, it must be the case that there exists the concrete environment whose evaluation is the concrete result, and the concrete environment must be a member of the symbolic environment. So this is it, the two parts of our correctness. And note here that it is a partial correctness, right? It depends on the fact that the evaluation must terminate. The symbolic evaluation must terminate to give a symbolic result. Now let's talk about the key invariants of SC, which will provide us with the ability to formulate queries. So there are several key invariants of SC that we identify. The three ones are reducibility, legality, and determinism. The first two, reducibility and legality, are pretty unique to our system. So what reducibility says is that symbolic evaluation reduces to concrete evaluation for concrete environment. And this property helps with the debugging. It means that you can test your interpreter on top of our reusable symbolic evaluator. Now, in fact, this property actually does not hold for the formalization that I just present. It requires a minor adjustment, and the details can be seen in the paper. It also requires cooperation from the symbolic factory so that the whole system is reducible. Legality states that symbolic states from symbolic evaluation are legal. In particular, you can interpret assumption implies assertions in the intuitive way. This helps aiding query formulation, right? Means that the interpreter can ask for these internal states and formulate the query at any time. Also, in particular, it means that the assumption and assertion cannot be both false at the same time, because we saw earlier how assumption is false corresponds to there's an abortion, and how the assertion is false corresponds to how there is an error. If they are both false at the same time, then we do not know if it's an abortion or an error, and so they cannot be both false. Determinism says that multiple runs of symbolic evaluation gives the same result, and this is obvious. So let me now give the results and evaluation. So we pose the following 3 research questions. Is the symbolic semantics reusable? Is the symbolic semantics general? And is the symbolic semantics efficient? Now, to show that the symbolic semantics is reusable, we plot 16 benchmarks from Rosette 3, which is an existing reusable symbolic evaluator, to Rosette 4, which is the implementation of our new symbolic semantics. And they all can be done. So this demonstrates the reusability of our new symbolic semantics. In particular, I would like to point out that due to the fact that we have this strong key invariance in the new symbolic semantics, we can simplify some solver-aided tools implementation significantly. Now, for the generality of our symbolic semantics, we demonstrate that by instantiating our symbolic factories with different symbolic factories. In the Leannet, we use a pretty naive symbolic factory. It only supports the data type of integer and Boolean, and the operations are unoptimized. By contrast, in Rosette 4, we use a very sophisticated symbolic factory. It supports numerous data types, and the operations are optimized. This demonstrates that our symbolic semantics admits a wide range of implementations. Lastly, we demonstrate the efficiency of our symbolic semantics. And this is done by comparing the performance of Rosette 3 with Rosette 4. So in general, the performance of Rosette 4 and Rosette 3 are pretty comparable. In fact, Rosette 4 slightly performs better. And for some of the benchmark, it performs really great. So, I mean, just to note that this is actually not our initial goal, right? We didn't actually intend for it to be much more efficient than the existing system, but this is kind of like a byproduct that we have. And so, yeah, that's it. This is the formal foundation for symbolic evaluation with merging. All the code and implementations are in the link that I present here, and you can see the formalism in the paper. Thank you.
Thank you. So do we have any questions from either people here in the audience or online? Do you have any questions online? So I have a question. So was there any expressivity that was sacrificed in order to get verifiability? Is there any feature or that was present in the original version that maybe is present in a somewhat different form here to make the verification go through?
So compared to the existing system, Rosette 3, actually our system is kind of more expressive. Yeah, it's actually strictly more expressive. So there is no expressivity sacrificed.
can you give an example of like what feature was dropped?
Right. So in particular, in the existing system, Rosette 3, we do not support the assumption statement in the language. And in particular, by adding the abort statement to the language, that allows us to express the assumption in a nice way. So yeah, this is one place where the expressivity is increased.
I see.
Also, another thing that I would like to point out is that in the previous system, so Rosette 3 already supports loop, but the correctness theorem in Rosette 3 kind of like assume that the loops must be unrolled first. Our formulation of correctness in this new symbolic semantics is a bit different, and it does not assume that. Yeah. So that's another difference.
Thanks. Any other questions? Okay,
Right.
so another question online. In listening to the talk, I was trying to translate to what I know about abstract interpretation. You had a notion of completeness, which one rarely has with abstract interpretation. How important is it, and have you tried working without completeness?
Yeah. So I mean, these tools again, it works by running the symbolic equation on multiple layers of tools, right? And we need, in order for the verification query to work, it needs to be both sound and complete. So yeah, abstract interpretation wouldn't work well here. Again, we are doing synthesis query and verification query here, right? So I mean, we need both sound and completeness here.
All right, thank you. So I think we're ready to move to the next talk, but let's thank the speaker first.